Okay, demonstrating the process of finding eigenvalues. And I thought I'd designed this matrix to have real eigenvalues, real integer eigenvalues, but apparently I screwed up somewhere. But we went ahead and did this anyway because it's a good illustration of one of the things that can happen. Remember that the eigenvalues are the values that solve the equation AV equals lambda V for some vector V. Okay, that's our general context of this entire discussion. So we're trying to find vectors that map to multiples of itself. So we're looking for solutions to the equation AV equals lambda V, where V is a vector. By rearranging this equation, it becomes A minus lambda I equals 0. Okay? And it has a non-zero solution if and only if that A minus lambda I matrix is not invertible, meaning that its determinant is 0. So we solve this for lambda. And the solutions are going to be what we call eigenvalues. Okay? So that determinant becomes this. It's very straightforward. A minus lambda I. Lambda I has lambdas on the diagonal. So when you add negative lambda I to this, you're going to get a negative lambda on this term and a negative lambda on this term. You're going to get negative 6 minus lambda, negative 1, 36, 5 minus lambda. The determinant of that should be equal to 0 so that the matrix equation will have non-zero solutions. So the determinant is just this times this minus this times this. Okay, I don't have to read that to you. You see where it comes from. Now we expand this. This becomes lambda squared plus lambda minus plus 6. Okay. I'm sorry. This becomes lambda squared plus lambda minus 30. Okay. And the minus 30 added to 36 leaves us 6. So this equation has to be satisfied in order to have eigenvalues. However, this equation can't be satisfied by real numbers. You can check out, this is a quadratic equation. Its discriminant is negative, so it has no solutions. And if you don't know what I mean by that, review quadratic equations and the quadratic formula and the implications, okay? So anyhow, there's no real solution. We tried to fix that and it didn't work well. So, in desperation, I didn't want to have to make up another one in my head or even on paper. I didn't want to take the time to do it right, and if I did it wrong, I was just going to be back where I was without an example. So I defaulted to a really simple example, which is still plenty illustrative. Okay, I went to this matrix. Okay, the A minus lambda I matrix in this case is just going to be, well, 0 minus lambda and 0 minus lambda is going to give us negative lambdas in the diagonal, and we got the 1 and the 36 on the secondary diagonal. Giving us a determinant of lambda squared minus 36, which is equal to 0. And that factors lambda minus 6, lambda plus 6 equals 0, so lambda is 6, or lambda is negative 6, and these are our eigenvalues. The eigenvectors, well, we use lambda equals 6. Remember, the equation that we're trying to solve is AV equals lambda V, right? So that, and I haven't written it down, I probably should. So let's kind of complete this. That means that A minus lambda I times V is the 0 vector, as we saw last time. It's a very simple rearrangement. So that our equation, a minus lambda I v equals 0, if v is the vector, choose to write our unknown vector v as the column vector x1, x2, okay? Then our a minus lambda I matrix is just this matrix with this value of lambda. Well, lambda is 6, so negative lambda is negative 6, so there's our matrix. Okay, so this matrix times our vector v would have to equal the 0 vector. That gives us two simultaneous equations. And as we saw before, both simultaneous equations turn out to have exactly the same solution, because this equation, the equation we get from the second row here is just going to be negative 6 times the equation we get from the first row. So going through those details and review or look at examples in the book, review the videos, review your notes from last time, this equation, or this matrix equation, reduces down to the equation x2 equals 6x1. Okay? And from that we conclude that v is some multiple of the vector 1, 6. Okay. Note that you can't invert this matrix. Why can't you invert it? Because it's of this form with the determinant of 0, right? The determinant of this matrix is clearly 0. So it's not invertible, but we easily solve it by writing out the corresponding equation. In this case, it would be negative 6x1 plus x2 equals 0. But again, I'm not going to belabor that. Okay, eigenvalue negative 6. Well, then our negative lambdas would be 6, and we'd have this equation. And both of the equations you get, first row times column equals 0, second row times column equals 0, both of those equations reduced to x2 equals negative, can be reduced to x2 equals negative 6x1, so that our eigenvector in this case is t times 1, negative 6. Letting x1 equal t, x2 equals negative 6t, and factoring out the t, there's the vector we get. Again, refer back to the details from last time. Okay? So this gives us two eigenvectors, 1, 6 and 1, negative 6. And we know that this eigenvector, this eigenvector will map onto a vector in exactly the same direction, but negative 6 times as long, or 6 times as long in this case, and here negative 6 times as long. Okay. So our eigenvectors are 1, 6 and 1, negative 6. And I can put these into a set and observe that this set is clearly a basis of R2. Okay, now if you have distinct eigenvalues, your eigenvectors are going to be linearly independent. And if there are enough of them, they'll span your space. They clearly span this one. These vectors are clearly linearly independent, because in R2, that's just equivalent to saying they're not parallel. I mean, okay? Now, when you have a bigger set in a bigger space, if you got 4 eigenvectors in R7, to determine whether they're linearly independent takes a little more work, but that's going to be sufficient here.